Hi everyone, welcome to another Select seminar, which is it's not the first of the series, so it was one last week. Okay. So today we have Marco Schumann, who will be talking to us about bridging wire and gate cutting with the Select calculus. So if you want to start, Marco, let's go ahead.
Yeah, so thank you for the invitation. And yeah, as you said, I want to present our new paper. And to do this, I want to spend the first two slides to explain a bit the rough idea of the paper and also what wire and gate cutting are. And so wire and gate cutting are tools for circuit cutting, which means that they allow you to take a quantum circuit and split it into multiple smaller quantum circuits. And it was introduced in these papers. And to understand it, you can look at an example circuit like this one here with 5 qubits that we represent as a ZX diagram. And then you can ask if you can use a quantum computer with a fewer number of qubits to run this circuit. And like in this example here, we assume that our quantum computer only has 3 qubits. And then you find that you can use circuit cutting techniques to cut this circuit into two smaller circuits. That is one circuit that only acts on the qubits in region A, and one circuit that only acts on the qubits in region B. And then you can run these two circuits on your 3-qubit quantum computer and effectively run this 5-qubit circuit. And on the next slide, I show more explicitly how to do this. And at this point, I also want to say that these techniques come with a limitation that usually you can only use them when you're interested in an expectation value on the output state here. Yeah, in particular, you can cut this circuit using wire cutting, as I show here, where the idea is simply that you can interrupt the wire by measuring and reinitializing the qubit in certain states. And you see that if you apply a wire cut here and here, this will allow you to split the circuit such that there is one circuit acting on the qubits in region A and one circuit acting on the qubits in region B. And the second technique that you can use is called gate cutting, which you can see here for the C0 gate. And here the idea is simply that you rewrite this gate as a sum of more local operations that can be more local gates, but that can also be, again, measurements and reinitializations. Yes, and you see that if you cut this gate again, this will allow you to split this circuit into two circuits. And when you use these techniques, you always have to pay a price. And this is that you need to run the circuit more often to estimate this expectation value at the end here than you would need to run the circuit if you would not cut it. And basically, the question that we ask in our paper is if there is a connection between these two techniques for circuit cutting that are right now mostly seen as independent approaches in the literature. And the way we study this connection is quite natural if you look at the circuit in terms of ZX calculus, because we simply ask if we can cut this wire in this gate here, and if this will allow us to get a gate cut. And yeah, indeed, we find that in many cases this is possible. And yeah, a feature that is good for us here is that in this ZX diagram, only the connectivity matters, which means that if we can cut this wire, we should also be able to cut the wire that is oriented vertically. And yeah, while this is conceptually interesting, it is also useful because it helps us to have a straightforward way to get protocols for gate cutting. And also we find that sometimes the protocols that we get by doing this are better than the ones that we know from the literature. Yeah, this is the outline of the talk. So in the first part, I will give a very short intro to ZX calculus. Also, I guess you all know it better than me. Then I will explain how to do wire cutting with ZX calculus in the second part. And in particular, there are two cases that I want to discuss, that is wire cutting without and with communication. And what this means here is simply that if you cut a wire, you measure the qubit in a state and then you reinitialize it. And if you use communication, it means that the measurement result will be used to decide which state you reinitialize. And it turns out that if you do this, then the sampling overhead that you have to invest is smaller than if you do not do it. And therefore, here we use wire cuts with communication. And in the third part, I will then explain how to use these different these wire cuts to cut different gates. In particular, the multi-qubit control Z gate, the 2-qubit ZZ rotation gate, and a sequence of single qubit controlled unitaries. Yeah, and in the end, I want to give a conclusion and an outlook. Okay, so let me start with the ZX calculus part. That is a graphical language for describing quantum processes. And here we use it to describe our quantum circuits. And in particular, you have these wires that carry qubit states, and you have these so-called spiders that can change the qubit states. And for us, it is convenient to also define this H box here that is not independent of these spiders. And for one input and one output wire, it corresponds to a Hadamard gate, or it is at least proportional. Then you can also define the bell states and the wire crossing, but more importantly for us, you can define initializations and measurements of eigenstates of Pauli matrices. And yeah, this we will need to define the wire cut in ZX calculus. And finally, here we show how to represent a CNOT gate. And we again stress the fact that only the connectivity in the ZX diagram matters. Yes, and as we insert the wire cuts in the ZX diagrams, the resulting diagrams will in general not automatically correspond to a circuit that we can run. So we need to use some rules from ZX calculus to turn the diagrams back into diagrams that correspond to circuits. And here I don't want to go over all the rules. Let me just say that this here is the fusion rule. That means that you can fuse spiders of the same color and add the entry. This here tells us that the H box will change the color of a spider. And here in F, I show the H box fusion rule. And this will be important for cutting the multi-control Z gate. Okay, so now let me explain how to cut a wire in ZX calculus. And to do this, I want to use this simple 1-qubit example circuit where you have an input state, then you apply two unitaries, and then you want to get the expectation value of an observable O. And we assume that we want to cut the wire between the application of U1 and U2. And so we can represent this expectation value like this with super operators, or we can write it in the Pauli transfer matrix representation. And since we use this Pauli transfer matrix representation in the paper, I quickly want to introduce it. Yeah. So this is how we label the qubits in our the Paulis in our system. And then we can define the normalized Paulis. And the idea is now simply that you write the density matrices as a sum over the normalized Paulis. And this then allows you to vectorize the density matrices where the entries are simply the weights in the Pauli decomposition. And you can do the same with your observable. And the quantum channels in the Pauli transfer matrix representation become matrices, which means that now you can multiply these matrices to these vectors, and this will simply shift the weight in the Pauli decomposition. And when you have this, it is now easy to see how you can define a wire cut in this formalism, because you simply need to note that the sum over the normalized Paulis like this is equal to the identity. And now the idea of wire cutting is simply that we insert this identity here between U1 and U2. And yeah, that's what I did here. And now you see that to cut the wire, you need to initialize your qubit. Then you need to apply U1 and you measure in the Pauli basis. And for the second term, you need to rewrite this sum here as a sum over the eigenstates of the Paulis. So, for example, the Pauli set will become 0, 0, minus 1, 1. And with this, you get this expression, where now you see that for the second part of the circuit, you simply reinitialize the eigenstates, you apply U2, and you get the expectation value of O. And now the idea is that you want to randomly sample from these circuits to get an estimate for this expectation value. And to make this happen, these prefactors here need to correspond to probabilities. But here they correspond to quasi-probabilities. And this means that they can, for example, take negative values. And you can apply two tricks to turn them into probabilities. The first one is simply write this quasi-probability as its sign times its absolute value. And the second trick is to define this so-called one norm. That is the sum over the absolute values of the quasi-probabilities. And we divide and multiply with this. And now you have this new expression, and you can check that indeed these prefactors now correspond to probabilities. And so what you can do is to simply sample from these circuits with these probabilities, and you will get an estimate for your expectation value of O. And yeah, this procedure is also very similar to what you do, for example, in probabilistic error mitigation. And yeah, in particular, you can check here that these probabilities are all 1/8. And this means that you need to reinitialize the different Pauli eigenstates, each with probability 1/8. And you have to measure in the corresponding Pauli basis. And yeah, then as I said, these techniques always come with the sampling overhead. And in particular, you can use Hoeffding's inequality to show that this sampling overhead is the square of this one norm, which is in this case 16. So it means that now we need to run the circuit 16 times more often than if we would not cut the wire. Yes. And as I said before, we can use communication in the wire cut to decrease this overhead. Because right now we do not use communication, because here we simply reinitialize the Pauli eigenstates and we will measure in the corresponding basis, but we do not use the measurement result to decide what we initialize. And yeah, if you look at this table, you will notice that our protocol right now has some form of redundancy, because we use the eigenstates of the Pauli Y for the Pauli Y, but also for the identity. So sometimes we will initialize the same eigenstates. And it turns out that we can use communication to remove this redundancy, and this will decrease the overhead of the wire cut. And in particular, you can consider the term from the identity and the Pauli Y. And you will see that in this Pauli transfer matrix representation, some terms cancel. And so in the end, what you need to do to realize this term is to simply measure in the Pauli Y basis and reinitialize the state that you measured. And yeah, this was explored in some papers. And with this, we can now write down the full protocol for wire cutting with communication, where here, this first map simply means we measure in the Pauli Y basis and reinitialize what we get. And these other maps mean that we reinitialize the eigenstates of the polys and measure in the corresponding bases. And yeah, in the second column, we say that only the first map is a completely positive trace preserving map, because for the other ones, we sometimes have to add a factor of -1 by hand to the contribution of the expectation value. And here in the very right, we show the different ZX diagrams corresponding to the channels. And so this means that if you want to cut a wire in ZX calculus, you have to insert these diagrams at the point where you want to make the cut. Yes, and you can also check that the overhead indeed decreased, because you can compute that here the one norm is 3, and so the overhead will be 9. While if you do not use communication, then the overhead is 16. And yeah, I also want to mention that here we decided to use the communication for the poly Y, but of course this is kind of an arbitrary choice, and you could also have used communication for poly X or poly Z instead. Oops, sorry. Yeah, so now I want to show how to use this wire cut to cut different gates. And I want to start with the MCZ gate that is represented in ZX calculus like this. And we assume that it acts on m plus a prime qubits, and we rewrite it with this H-box fusion rule, like shown on the right side here. And you see that it is in a useful form for us, because now we can cut a single wire to cut this gate between the upper M and the lower M prime qubits. And if we do this, we simply insert the ZX diagrams for the wire cut now, and we get different diagrams from the different diagrams of the wire cut. And I first want to say that we defined these variables here, a y, a x, and a z, and they can take the value 0 or 1. And it corresponds to the different eigenstates of the polys. And since we use communication for the poly y, you see that we use the same variable for the upper and the lower qubits here, while for the poly x and for the poly z, we have additional variables. Since here, in principle, you can have a different eigenstate than for the upper qubits. Yeah, I also want to say that these diagrams do not always directly correspond to circuits. This one, for example, does, because it's simply a multi-control phase gate of this angle, but this one does not. And we then use the ZX calculus rules to turn them back into diagrams that correspond to circuits. So for example, here we use the fusion rule to rewrite it like this. And it means that we can simply realize it by initializing an ancilla qubit in plus, then applying this multi-control Z gate, and then measuring the ancilla qubit in the X basis. Yes, then sometimes it also happens that the scalar that comes with the diagram does not give the correct normalization, like here. This is the only one of these 6 diagrams that is not correctly normalized. And in particular, it is missing a factor of square root 2. And it turns out that we can add this factor if we multiply the probability to call this diagram by the inverse of the absolute value squared. So here it means that we need to multiply the probability to call this channel by 1/2. And yeah, finally, I want to say something on the role of the communication here, because you see that we inserted a wire cut that requires communication for the poly Y. And but now the resulting protocol does not need communication, because what it tells you here is simply that you need to put the same rotation angle for the upper and the lower qubits. But we can simply fix this before we run the protocol. Yes, and with this we can now write down the protocol for the gate cut, where here the first two lines simply correspond to this left column here, which means that you apply this multi-control phase of plus or minus pi half. Then the next two lines correspond to this poly X, where for the upper qubit, you take this ancillar qubit, you apply the MC set, and you measure the ancillar in the X basis, and the lower qubits, there we need to apply an identity or the MC set. And this is defined in these two lines, and this is the channel with the ancillar qubit. And yeah, for the last two lines, it's from the poly set, and it's very similar. So what we see from this is that we can cut the multi-control set gate by cutting a single wire. And this will come with a one norm of 3 and require a single ancillar qubit. And we verified numerically that this decomposition is indeed correct in our GitHub repository. And there we also checked the other decompositions that I will show you later. Yes, and I also want to mention that this gate was been cut before with ZX calculus. And in this paper, they used a different approach than we, because they did not use this idea to cut gates by cutting wires, and therefore they get a bit of different protocol. And in particular, in the protocol they show, they get a one norm of 6, but they do not need ancillar qubits. And then they also say that they could decrease this one norm if they use ancillar qubits and use post-selection, but they did not do it. And also we do not need post-selection here. Yes, so then,
Can I just
yeah,
ask some
sure.
clarifications? I'm a little bit unsure how this Pauli representation thing gets translated to ZX, because like I guess you're working with channels, so you're kind of doubling up the diagram, right? Like why are we getting like the X, Y, and Z in the ZX diagram instead of just we cut a wire so we get like a measurement in say the Z basis or the X basis instead of getting it on all the bases?
Okay, wait, maybe we can use this, right? Um, yeah, so basically that's how we translate the measurement and the reinitialization to the diagrams, right? Can you maybe ask the question again? I'm not sure if I understood correctly.
Yeah, I guess my confusion is why do you get so many different maps? But I think that's because you're dealing with channels, so you have everything doubled up instead of working with pure maps, since you care about probabilities.
Um, so, okay, so you think there should be less maps in this table?
No, it's like if I have a ZX diagram, right, and I cut a wire,
Hmm.
that will require a single variable, like that will have two outcomes.
But you measure in each basis, so you need to measure in the Z, the X, and the Y basis.
Yeah, so my question is, what's the equality on ZX diagrams that does that? Is I guess my question.
So I think if you would want to write it as an equality, then you have a wire on one side, and then you have the equal sign, and then you need to sum all the terms on the right here.
Okay, so you're instead of decomposing identity into two terms, you're decomposing identity into 8 terms or 16 terms, with like smaller constants in front of them, I guess.
Yeah, so there are many terms in the decomposition, yes.
Yeah, I think for like the diagrammatic approach, this needs to have like doubled diagrams where you can represent mixed processes. But yeah, that's fine. Um, yeah, I guess my second question. If you can go to the next slide, the next
Hmm.
slide, next slide. Yeah, this one. Um, so what happens if you get the wrong outcome in, for instance, this one where you do an ancilla, then a CCZ, and then a measurement in the X basis? Like what happens if
You mean this one?
yeah.
I mean, there is no wrong outcome, I would say.
Oh, right, because on the bottom you do different things depending on your outcome.
Yeah. So,
Yeah.
and also you need every combination. So you need ax equal 1 and ax prime equals 0. And yeah, so here it's no problem.
Okay.
Only for the y, you need the same spider for the upper and the lower qubits. But it is fine because it is the rotation angle.
Yeah. Yeah.
Can I add one thing?
Yes.
So this AX, what it determines is actually the sign that you have to put in the estimator. So the outcome on the top determines whether you get a plus or a minus. It's no, you can't see it from the diagrams, but yes.
So
Yeah, so
you're sampling many times, and if you get the one outcome, you add it, and if you get the zero outcome, you
Yeah.
subtract it. Yeah.
Yes.
Yes.
Okay, thanks.
Okay.
Could I ask a question?
Yes.
So actually this is a good slide for it. So I didn't really understand when you categorize some of these things as CPTPs and some of them as not CPTPs. So it looked like all of the different channels you're running are runnable, non-deterministic processes. But so what did you mean by saying that some of them are not? Do you mean that they're just different branches of something that's non-deterministic when you say no, that's not a CPTP?
I think the point is that if you, for certain measurement results, you need to, so the measurement result will decide if you subtract or add the contribution to the expectation value.
Okay.
And yeah, that's why we put it here.
Okay. So if I didn't do this adjustment for the signs, if I just mixed those two processes together, that would be a CPTP.
I think so.
Yeah. Okay, that makes sense. Thanks.
Okay. Are there more questions or should I continue? Okay, then let me go to the next gate that we cut. That is this 2-qubit Z rotation, where again it is in a form that we can cut it into two parts by just cutting a single wire. And this is what I will do in the first step. I will show how to cut this gate to get a gate cut with 1 norm 3. And then in a second step, we realize that in the literature, it has been shown that this gate can be cut with the smaller 1 norm. And I will show then in the second step how to reshuffle the channels in our protocol such that we also get this optimal 1 norm. Yes. So now first I insert again the wire cut and I get these different diagrams for the gate cut. And you might note that now I exchange the role of the poly X and the poly Y. And the reason for this is that here for the poly X, we just need gates. And for the poly Y, we need an ancilla qubit and a measurement. And so if I would use communication for the poly Y, I would need to take this measurement result and communicate it to the upper qubit to decide the rotation angle. And so we decided to use communication for the poly X here, because here again, it's just two gates, and then the gate cutting protocol will not require communication. Yeah, then again, this diagram here is not correctly normalized, and we can normalize it by adapting the probability. And this will make the probabilities dependent on the rotation angle because this scalar is dependent on this angle. And yeah, again, we get different maps in the protocol. The first two lines simply correspond here to applying the identity or a rotation about pi. Then the next two lines correspond to this poly Y, where here you have to apply a rotation. And here you need to take an ancilla qubit, apply the RCZ, and then measure it in the Y basis. And then the last two lines correspond to the poly Z. Oops. Where here we simply reinitialize what we measured And for the lower qubit, we apply rotation. And yeah, this gives the gate cut with 1 norm 3. And as I said, this 1 norm can be decreased. And in particular, what you need to do is to rewrite the sums of these maps such that the theta dependence goes out of the map and in the quasi-probabilities. And you can, for example, show that the difference between these rotations is the sinus times the difference of these pi-half rotations, or this map with the ancilla qubit simply corresponds to reinitializing the qubit in what you measured and adding this sinus. And yeah, with this we can decrease the 1 norm and also get rid of the requirement of the ancilla qubit. And yeah, then you can check that this protocol indeed has the optimal 1 norm. Yes. And now as a last example, I want to show a sequence of single qubit controlled unitaries. And in particular, here we have one control qubit and many controlled unitaries. And we use the fusion rule to rewrite it like this, such that we can separate the control qubit from the rest with a single wire cut. And again, this gives different diagrams. And you can note that now we need an ancilla qubit for every term for the lower qubits. And we need to initialize it in plus, and then we need to measure it in the end in a certain basis. And so now this means that here we cannot easily get rid of the requirement for communication because each Pauli has this measurement. And here we communicate for the Pauli y, and this means that you first need to apply the measurement here, and this will tell you which rotation angle to put for the upper qubit. And yeah, again, this factor needs to be adapted. And this is then the protocol that we get, where the first map is simply for the Pauli y, and it requires communication, which means that if we measure the ancilla qubit in plus I, we apply a rotation of plus pi half. And if we measure the ancilla qubit in minus I, we apply a minus pi half rotation. And yes, the next two lines are this Pauli x, where you apply the identity or an Rx rotation, and you do this thing with the ancilla qubit for the lower qubits. And yeah, finally, the last line is for the Pauli set, where we reinitialize what we measured, and we again use the ancilla qubit for the lower qubits. Yes.
Sorry, Mark, can you go back to the one slide deck?
Yes.
But at the bottom right, why wouldn't you just copy this pi phase through all the things and get rid of the control wires? So it just
Here.
becomes on the top one you measure, and then depending on the measurement outcome, you either perform the D1 to DM or you use them as identities because they're controlled unitaries. Like, well, why? Because like right now it looks like both of these are dependent. Like you have this AZ and AZ prime, but you want them to be equal, right?
Here.
Yeah.
No, it does not need to be equal. I mean, we
Okay.
could use communication for the set term, then it should be equal.
Okay, but then in any case, you can still simplify the bottom right? You can just treat them as if AZ prime is 0, you do identity, and if AZ prime is pi, then you just compute these unitaries like without the controls, just like directly on the qubits.
Ah, okay, so you say I could use this ZX calculus rule here?
Yeah, just like pi copy.
Yes, I think it should be possible. Yes. Yeah, maybe it's not the only way to put this diagram.
Yeah, I mean, unless you want to treat these controlled unitaries as black boxes where like you can't get rid of the control, like then this will be fine. But if you say like, oh well, I know like oh these are Toffoli gates or something,
Mm,
then like doing this copy rule simplifies them to CNOT gates, for instance,
okay, I see.
removes the control.
Makes sense. Okay. Yes, then let me anyway conclude. So in the paper, we showed that different gate cuts can be obtained by applying wire cuts in ZX calculus, which is conceptually interesting, but because it means there is a connection between wire and gate cutting. We found that sometimes the requirement for communication can vanish, which means that we insert a wire cut that requires communication, but the gate cut that we get in the end does not. We found an improved cut of the MCZ gate, and we showed how to cut a sequence of single qubit controlled unitaries. And as an outlook for future things we could do, first of all, it would be interesting to find other scenarios where it is useful to cut gates by cutting wires. Then we wonder about the generality of our approach, because as we insert these wire cuts, we in general get diagrams that do not directly correspond to circuits. And now for the examples I showed, we always manage to turn them back into circuits, but we are not sure if there is a way to check the generality of this approach. Yeah, also we would be interested in improving the applicability of what we do, because right now every step requires still a lot of human thinking, and maybe it can be automated a bit. And finally, there's some literature on that if you cut multiple wires together, it is cheaper than to do it one by one. And the same is true if you cut multiple gates together. And so now we wonder if we could extend our approach to cut multiple gates together by cutting multiple wires together in ZX calculus. Yes, that's basically it. And I also have 2 slides of the literature in case someone wants to see the papers.
All right. Thank you very much, Marco, for the nice talk. We already had quite a few questions during the talk, but perhaps there are now other questions in the audience as well. Yeah, Sarah.
Thank you very much for the talk. I wonder, because in circuit synthesis, we have very efficient algorithm for Toffoli-Hadamard circuits on up to 3 qubits. And let's say if you give me a large circuit, is it possible to use your method to give us the cutted version of the circuit with sub-circuits containing as many Toffoli-Hadamard gate as possible with 3 wires, or at most 3 wires?
So wait, you want to cut a circuit with Toffoli and Hadamard gates,
Yes.
right?
Yes.
So why do you want to cut it? Because you want to reduce the number of qubits involved, or?
No, because for synthesis, we have very efficient algorithm for Toffoli-Hadamard circuits using some number theoretic results, but it's very difficult to generalize the synthesis to beyond 3 qubits. So I wonder if your cutting algorithm could be adapted to this like Toffoli-Hadamard gate set. So we can cut a large circuit into sub-circuits containing only Toffoli-Hadamard gates, and then we can apply the synthesis algorithm.
Ah, okay, I see. But how would you get rid of the gates that are not Toffoli or Hadamard?
Suppose you're given a circuit contains only Toffoli and Hadamard gates, but they're not very nice because you have a lot of like entangled part. You cannot really separate them into 3 qubit sub-circuits.
I mean, I guess in principle you can cut the circuit, and then you can maybe simplify the cut versions, but I'm not sure how. I mean, then you probably want to put it together again, right?
Yes.
I think I'm not sure, maybe.
Because in your cutting algorithm, you already consider the entangle gate and also this MCZ gate, right? Or it's quite different from. the Toffoli gate.
Yes. I mean, you can also just cut your circuit along wires, probably, right? You do not need to cut. Yeah, okay, I see. Yeah, I don't know how to. Right now, I don't know if it works, maybe.
Okay, thank you.
Yeah, I have a question. Have you thought about cutting spiders rather than just cutting wires? So, I mean, this is equivalent to say, a spider is basically a GHZ state. So it's trying to find a decomposition of a GHZ state as an affine combination of product states.
Mm,
And then you sort of, so rather than cutting kind of one of the legs of the spider, you sort of cut straight through the spider. Is that something you thought about?
no.
Okay. So we do that quite a bit for classical simulation, because this works quite well at the level of linear maps. So rather than at the level of channels, because a spider is always, at the level of matrices, it's just a sum of two product states.
Ah, I see.
But it's more complicated than if I think of the density operator associated to a spider. Then I think you would need more terms.
I see. Yeah, so I have not thought about it, but it's interesting. I mean,
So, yeah.
then there are probably also different ways to cut the spider, right? Because it depends which output legs you separate.
Well, yeah, I mean, so you could say I don't need to fully separate the spider. It could be I've got a decomposition which would kind of cut off all the legs at once, but you could say, well, maybe I just want to cut the spider in half, which means writing the thing as a affine combination of, say, like a 4-qubit state and a 3-qubit state or something like that.
So is there a connection to the wire cut? Because when I apply the fusion rule, then I could also cut the spider by cutting a wire, right?
E Yeah, yeah. So you could always make a partition of the legs into two. In that way, you could unfuse the spider and you could cut the wire. Um, I'm just wondering if there's some advantage to cutting it into more pieces at once.
I see. Yeah, I don't know.
Isn't this kind of what you did already with the controlled gates? Because like you had multiple Z spiders in a row, but it's essentially if you fuse them, it's a single spider. And then you cut it along one of the wires, sort of unfusing one of the legs. Yeah, like this thing. I mean, this is
Hmm.
essentially cutting the spider, right?
Yes. I mean,
Yeah,
it's in a very specific position.
Yeah.
yeah.
So I have a question about the applicability of these methods. So, of course, like did all these things must necessarily scale exponentially in the simulation and in the number of samples you need. Like that's just the way this method works.
Hmm.
Um, are you aware of people that have used this like in practice, where like it sort of survives this exponential scaling because the benefit you get by splitting it up into multiple independent sections just outweighs that, or maybe showing that certain types of circuits are efficiently simulable because they have few enough connections that you can like break them up in this way.
So if you're interested in something that did it in an experiment, I think that the other paper on cutting the MCZ gate, they also run experiments. Yeah, so apart from that, I'm not sure.
Like just spitballing, right? Like people care a lot about this quantum volume benchmark nowadays, which is like what's like the largest circuit I can run on my quantum device. Like, could
Hmm.
you imagine like, oh, I do some very special cuts so I can make my large circuit look like a smaller circuit, so I can just use my best qubits. And maybe it's a superconducting device, so it's super fast and running the samples needed. So a little bit of exponential blow up is not that bad. In the same way that error mitigation is exponential blowback as exponential scale up, but people don't care because they like the thing is fast enough. Oh, they
I
do care,
mean,
but like it still works.
I think it really depends on the circuit, right? If you only have to cut a few wires or gates, it's probably fine. But if there are many connections between the different parts you want to separate, then it will become too much at some point.
Yeah, so for these random unstructured circuits, like it's not going to work very well. Like you want to have the structure where the number of interactions between two regions is minimal.
Yeah, I also think so.
So maybe I missed it when you discussed about the resource overhead. Have you looked at how different cutting strategies would impact the use of ancillary qubits? Like, have you observed how ancillary qubits would grow while you're using different cutting methods?
Um, I mean, the reason we get ancillary qubits if we so in our paper is just because we do not manage to turn the diagrams back into reasonable circuits without using them. But usually then you don't need many ancillary qubits because you just like here you just need one to make this a circuit again. And yeah, so yeah, I don't think the number of ancillary qubits you need will grow more and more. It will just either be none or a few for a single cut.
Thank you.
Okay, are there any other questions?
Yeah, I just have a comment. This might not work, but just a kind of a half idea about how you can maybe solve this problem. You know, how you said that there's no way to know kind of automatically if cutting is going to result in things that are circuits, right? You kind of have to
Mm.
do this in these special cases. Some of the theory around G-flow might be able to help you there. Do you know about this stuff like generalized flow?
So I read the term somewhere, but I did not really look into the papers.
So this is something that works for ZX diagrams. It doesn't nec it's more difficult with H boxes, or there's less that's developed there. Uh,
Hmm.
but basically, if the graph of a ZX diagram has this combinatoric thing called G-flow, then
Hmm.
the thing will always you can always efficiently turn it into a circuit, and this doesn't depend on the parameters on your nodes.
Ah, okay.
And there's certain kinds of things like, particularly there's a variant called Pauli flow, which says that there's also certain nodes which you can delete them, and the result still has Pauli flow. So this might be able to use some of these kinds of results to argue like, okay, well, if I delete these nodes from my ZX diagram, if I started with a circuit, I delete these nodes, then the thing is still going to be equivalent to a circuit somehow.
Okay, thank you. I will look into it.